Okay, I'm going to start the recording. We learned about section 2.6 about derivatives and rates of change. And we learned that a derivative, the value of a derivative is the slope of a tangent line to a function at a certain point. And we have several definitions that we've learned that can help us find that derivative. So the book has some examples on finding derivatives, and I wanted to do a problem that's, it isn't one of our examples in the book, but you'll see it in the homework. Let me give you a moment to copy this example down. Okay, so in this example, we want to find the equation of a tangent line to the, let's see, that's a parabola. Let me see, hold on, I want to just check that if they, I got this example from the book. It's similar to one of your homework exercises, and I want to make sure that we should. That's not a parabola. That's not a parabola. We'll just call that. That's a curve. So let's fix that. Hold on here. I can do better than that. Okay. So we want to find the equation of the tangent line to the curve at the point 2, 2. Now we know that we could graph this function, this rational function, find the point 2, 2, because the point 2, 2 is on the rational function. Because if you let x be 2, 5 times 2 over 1 plus 2 squared, that's 10 over 5, that equals 2. That equals 2. Hold on, let me get a little bit better. So when x is 2, y is 2. So that point is on this curve, and we could draw a tangent line to the point 2, 2 on the curve. That's the equation they want. They want the equation of that tangent line. For any line, what do we need to find? For any line, what's necessary to find? The slope. Good. Excellent. And in Calculus 2, What's another name for the slope? Slope is a simple name for a derivative. That's right, Kelvin. So we're going to find the derivative of this function at x equals 2. Okay, so I will move to the next page then. So we need to find the slope of this tangent line at x equals 2. To this end, we must find for our function the slope or derivative f prime of 2. And this is the definition that you learned yesterday, okay, for a derivative. Let me give you a moment to copy it down, okay. Okay, so, all right, so is everybody okay up to this statement here about f prime of 2? Is everybody okay with that? That's the definition for if we want to find the derivative of the function at 2, we denote that by f prime of 2. Okay, we have a little symbol here. It's called a prime symbol, and that stands for the first derivative. Incidentally, if we wanted to take the second derivative, we would have 2 primes, but we're just worried about 1. Okay, so by the definition in the textbook, this is how we find the derivative. It's the limit as h approaches 0 of the function evaluated at 2 plus h minus f of 2, all divided by h. So that's a quotient. You're taking the limit of a quotient. And this is one reason that you learned a lot about taking limits, because derivatives a derivative is a limit. So what we have to do now is compute the limit. So what we have to do, of course, is f of 2, we know f of 2, we would just substitute in 2 for x. F of 2 plus h, we have to substitute in 2 plus h for x. Okay, and so the limit then becomes this. And you notice I'm carrying the limit sign. I'm not like dropping the limit. I am bringing the limit with me as I do the work. Okay, that's part of showing good work, good notation, and I'll be looking for that on your exam. Are there any questions so far? Oh, where does the 0 come from? Well, that's part of the definition, Ian, for the definition of a derivative. It is the limit as h approaches 0. And h will always be approaching 0. Okay, for the definition of a derivative. Okay, very good, very good. Good question, Ian. So now what we have to do is we have to find this limit. We have to find the limit. And it's a matter of just algebra. It's a matter of algebra. We can't compute the limit now. The expression, this expression, is not in simplified enough form. Okay, it's not in simplified enough form. But I see here that in the numerator, we have the difference. We have the difference of two fractions, right? We have the difference of two fractions. One fraction minus another fraction. When you subtract fractions, how do you subtract fractions? What do you need to find? What do you need to find? A common denominator. That's right, a least common denominator. Good, Zoe. Good, Joe. So okay, well, we're going to do what we need to do then to get a least common denominator. So, of course, I have to work out this expression on the left. I know that 5, like on the right, 5 over 2, or 5 times 2 over 1 plus 2 squared, that equals 2. No problem there. And I'm just going to let the 2 there. But on the expression on the left, I have to simplify that out. So I do have 2 plus h quantity squared in the bottom, in the denominator. So, okay, I can write that out like I do here. All right, give you a moment to copy that. All right. Are there any questions so far before we continue? Let's see. Lynn asks, would you have to foil the bottom factors, or could you leave as is and cancel the 2 plus h in the top and bottom? Good question, Lynn. You cannot cancel this 2 plus h. Let me put it in red. You can't cancel this 2 plus h here with this 2 plus h. You can't do it because you have the plus 1 there. In order to cancel, everything has to be multiplied. Every factor has to be multiplied by the other factors. So can't do that yet. What we're going to have to do is we're going to have to combine 1 plus 4 plus 2h plus 2h plus h squared. We're going to have to simplify that. That's going to have to be our next step. Okay, and this here, when you simplify that, what are you going to get? You're going to get h squared plus something plus something. That's right, Ian. H squared plus 4h plus 5. And so that's what we're going to get in the denominator. And if I go to the next page, okay, I have that on the next page. F prime of 2 then is going to equal this limit here. And so now we can't do anything more with this expression here, this rational function of h here. We have 10 plus 5h over h squared plus 4h plus 5. That's the best we're going to do. And remember, the 2 on the right is 2 over 1. So the least common denominator, the LCD, is going to be h squared plus 4h plus 5. That's what it's going to be. And so this will be our next step here, to multiply the 2 by h squared plus 4h plus 5 over h squared plus 4h plus 5. Take a moment, copy it down. Are there any questions up to this step here? And actually, I think I can show the next step because it's obvious. It's obvious what we're going to do. And this is the kind of work I'm going to need to see on your exam. Okay. And I'll try to give some, I mean, like a few of you had mentioned that like in section 2.5, some of those limits, a few students were using their calculator to get the limit, but I'm the right way, I want to say it the way I want to say it. The way that you learn in 2.5 to compute the limits for some of those limits is to do it algebraically, and I would expect that on your exam. And you know, again, this I may have to be you know, I want to be clear, but I don't want to tell you, you know, sometimes if I give too much information, I'm actually helping with the problem, you know. But again, this is something I'll have to think about. Exam's not till Monday, right? So, okay, are we okay up to here? All right, good. Now, what's the next thing we have to do? Thank you, everybody. What's the next thing we have to do? I mean, what's sort of the obvious thing? Combine. We have to combine these terms here in the numerator. So these derivative problems are not quick problems. It takes a little time to figure out what to do next. But if you take your time, usually it's an intuitive process. Okay, so I'll move to the next page then, if I may. Everybody's good so far? And you notice I'm putting a big old line here to separate out my numerator and denominator. I like to keep things clear in my work. Okay, so the minus 2 will get distributed here. The minus 2 would get distributed. And so this would be the next stage of the work. And then I still need to combine these 5 terms here. 10 plus 5h minus 2 squared minus 8h minus 10. Need to combine the like terms. Oh, thank you, Yaki. Yaki, notice the 10s cancel. Okay. That's good. That's good. And so, and then, oh, we can combine Kelvin's right, the 5h minus 8h. So here in the numerator, what are we going to get here? We're going to get negative 2h squared, negative 2h squared, then what? Good, thank you everyone. Negative 2h squared minus 3h. Okay, and so that's right, minus 3h. Okay, and so okay. And incidentally, oh yeah, I have an h. That's an h. Thank you, Rodrigo. That I mean that to be an h. Minus 3h. Okay, thank you. And in the denominator, you know, so I'm looking at this problem. I'm looking at this problem here. And I see in the numerator, I have a fraction. Now, if the numerator is a fraction, what might I like the denominator to be? If the numerator is a fraction, what would I maybe like in the denominator also? A fraction as well. Well, I have an h. That's right, Sebastian. I have an h. But could I write the h as a fraction? Yeah. Well, Ian, I don't want to multiply by 1 over h, but I want to write it as h over 1. But then, okay, I see what Ian's saying. Ian's saying you have a fraction divided by a fraction. So you could take the top fraction and multiply by the reciprocal of the bottom fraction. That's right. Okay, so we can do that. We can do that. So our derivative, f prime of 2, is going to equal then this expression here. It'll be the limit as h goes to 0 of the numerator fraction, negative 2h squared minus 3h over h squared plus 4h plus 5, times the reciprocal of the denominator fraction, which will be 1 over h. That's equivalent, incidentally, to multiplying, as Ian was commenting, that's equivalent to multiplying the numerator and denominator by 1 over h. Absolutely. Okay, and so we're this derivative, which in the beginning looked a little scary, we're making it look nicer. Okay, we're making it look nicer. Because what I'm going to do here, in the negative 2h squared minus 3h, I'm going to factor out an h. So the numerator will become h times negative 2h minus 3, and then the two h's simplify out. Giving me, you know, something nice. Okay, so f prime of 2 f prime of 2 okay, f prime of 2 equals the limit Well, we're not quite there yet. We're not quite there yet. Well, Nicholas, you are right. To get the tangent line, we will, once we get the slope, then we'll use the slope and the 0.22 to get the tangent line. But all right, so f prime of 2 is equal to this limit here on the right. What would that limit be as we let h goes to 0? What are we going to get? What's going to happen? What happens to the term negative 2h as h goes to 0? What's that be? Okay, that goes to 0. H squared, what's that go to? That goes to 0. And 4h, that goes to 0. So you're left with negative 3/5. So f prime of 2, trying to write it as nice as I can write it here. F prime of 2 equals negative 3/5. Now that's the slope. That's our slope. And we'll get to this picture here on the right in just a moment. That's our slope. And what that is, it's what I've drawn is here. Well, actually, I actually got it from the book. It's the right picture though. This is your function. So thank you, Kelvin graphed it on his calculator already, and he confirms that this is your function f of x. Okay, this is your function f of x in the blue here. That's your function f of x. And what they've done is at the 0.22, which is right here, at that 0.22, they've drawn a tangent line through the 0.22. Okay, that's the 0.22. And you can see this, the slope of that tangent line going through the 0.22, is it positive or negative? It's definitely negative. Well, it goes down. The tangent line goes down, so it has to have negative slope. So the tangent line, that's okay, John. I like all answers, you know, here in the chat window. It's good, participation's good. So in the picture here, in this picture, they've drawn the function f of x in blue, and they've passed a tangent line through, well, they have a point then, the 0.22 is on this function f of x, and they've drawn a tangent line to the curve, to the function at the 0.22, and the slope of that tangent line is negative 3/5. That's what they have here. Okay, are there any questions? Now we have to get the equation of the tangent line. But are we okay so far? All right, good. Well, we have the slope, we have a point, we have a slope of the tangent line, we have a point on the tangent line. Okay, we can get the equation of the tangent line by the point slope formula. Okay, so you remember y minus y naught, or y minus y sub 0, equals m times x minus x sub 0. That's the point slope form of line. And that's what we're using here. The slope is -3/5, and the point is 2, 2 that the line passes through. This is just algebra, basic algebra. And in the end, the slope of that tangent line is going to be y equals -3/5 x plus 16/5. Okay, are there any questions? Nicholas says fantastic. I agree. I agree. It is one of the most beautiful things you're going to see in your life, I would say. Okay. Okay. Lynn's a little skeptical, but oh, how do we get the 6/5? Neil asks. If we just, so the -3/5 distributes on the x and the -2. That's right. And so -3/5 times -2 is +6/5. Okay. Are there any other good questions? All right. Okay, well, I'm gonna upload some more notes from section 2.6. So I'll need to, can I go back? All right, hold on, Trevor. Let me go back one page. I'll come back here. All right, are you good, Trevor? All right, good. All right, so may I, is everybody ready to move on? Are we good? All right, excellent, excellent. All right, so let's do another couple problems here from section 2.6. All right, let me bring it up. I have to bring it up. I have to share the files. One moment here. Let's see. Just got to get it. Okay, let me see here. I'm learning all these notations now that people use in their text messages, like I guess TX means thanks, and YE means yes. Facts. Okay. 10x also. These are things I don't know what they exactly mean. Oh, thanks. Oh, 10x is thanks. Oh, wow, I would have never gotten that. Okay. All right, let me see here. So let me see, the file should be here. Okay, this is the one I want. Okay, so we just did this problem. Okay, I want to actually point something out in the ebook here. So there are applications to derivatives, and one of the applications that's important is velocity. Now, up to now, you've been finding velocities like average velocity. Okay, so the velocity, of course, if you wanted to find the average velocity, you would take, like if a particle moves from one point to another point, to get the average velocity, you would take the difference of the positions divided by the difference of the times. The particles at one point at a certain time, and then it moves to another point at a certain time. So the average velocity would be the displacement, the difference of the positions, and divided by the difference of the times. Okay, how many recall doing that kind of thing in maybe in a previous class, pre-calculus, or maybe one of your other classes? How many remember finding average velocity? Okay, so a number of you do. So, well, now what we're going to do is find instantaneous velocity. Instantaneous velocity, what's the velocity of a moving object at one particular time, at that instant of time? That's what hold on, I'm in the wrong thing here. Hold on. One moment. I don't want to be, let me get out of that. Let me go back. Yeah. Okay, so so you already dealt a little bit with velocities in section 2.1. 2.6 here, let me bring up the velocity. Now hold on here. So Lynn, it's an instantaneous rate of change. That's exactly right. That's what we're finding. So average velocity, and this is in the book, average velocity is defined as displacement over time. Okay, and if your position function, they're saying here in general, suppose an object moves along a straight line according to an equation of motion, S equals F of t, where S is the displacement. The function that describes the motion is called the position function. Okay, and so in the time interval from t equals a to t equals a plus h, the change in position is f of a plus h minus f of a. Notice we got that h. Okay, we got h again. Remember, we had h in the definition of our derivative, and we let h go to 0. Well, this is the same h that we're talking about. So average velocity would be the difference in positions, f of a plus h minus f of a, divided by the time, which is h. So if you go from time equals a to time equals a plus h, you subtract those times, you're going to get time h. So what we want to do here, this is figure 6, and it's in your ebook. Figure 6 shows you the average velocity, which is the slope of the secant line going through the points P and Q. And you've seen secant lines before. You saw this actually in section 2.1. But now what we want to do is we want to get, instead of average velocity, we want to get instantaneous velocity. So to get the instantaneous velocity, okay, that is going to be the limit of the average velocity. Well, I want to be clear. If we want the instantaneous velocity at time equals a, okay, that instantaneous velocity would be found by letting h go to 0. Okay, that's how, because you see the way the velocity is defined here, the way the average velocity is defined, is basically that's the quotient that's involved in a that's the quotient that's involved in a derivative. Okay, that's like if you think about the problem we just did, the problem we just did, we had f of 2 plus h minus f of 2 all divided by h, and we let h go to 0. But that was the derivative. Well, the point is, the way average velocity is defined, you have this quotient, and if we let h go to 0, the instantaneous velocity would be what we're finding, and that instantaneous velocity is going to be the slope of the tangent line to the curve at time equals a. So therefore, the instantaneous velocity it has this definition: the limit as h approaches 0 of f of a plus h minus f of a over h. And the little f function, the f function is your position function that describes the position of your object at time t. Okay, so that's what instantaneous velocity is. And you see, it's a very natural application for a derivative because of the way average velocity is defined. Are there any questions on that before we get to our example? I thought it was good to sort of give you just a little intro on that. Okay. So that's right, Kelvin. Instantaneous velocity equals derivative. That's correct. Okay. Very good. Well, all right. Well, let's apply this concept to a problem here. Let's see here. So this is the one I want. Okay. Whoops. All right. So here's an applied problem. Let me give you a few moments to copy the problem down. Okay, so, all right, in this example, if a rock is thrown upward on the planet Mars with a velocity of 10 meters per second, its height in meters after t seconds is given by the function h, which equals 10t minus 1.86 times t squared. Okay, that's what the function h is. And for this problem, we want to find the velocity of the rock after 1 second and after 4 seconds. Okay, we want to find the velocity after 1 second and after 4 seconds. And then with what velocity, they're asking with what velocity will the rock hit the surface? And I'm just checking one thing here, one moment. One moment on this. Yes, okay, everything's good. Okay, so, all right, so when they say in this problem, find the velocity of the rock after 1 second, they mean at 1 second, right at 1 second. And then find the velocity of the rock after 4 seconds, they mean right at 4 seconds. So they're not looking for average velocities, they're looking for instantaneous velocities. Okay, and instantaneous velocity means we're going to have to find instantaneous velocities. What do we need to compute? What do we need to compute to find instantaneous velocities? Slopes, that's right, Lynn, and slopes are the same as, that's right, Sebastian and Lynn, derivatives. Okay, so let's go ahead to the solution here. Okay. Now what I've done here is you don't have to copy this picture down right here because it's going to be drawn later on for you, but I've just drawn, you know, a picture of this h function. So remember what we're doing here. We're on Mars. We're like you know, what was that movie? The Martian, the guy who's on Mars. What's his name? The Martian. Yeah, that's right, John. Matt, is it? Can't remember his name. Matt Damon. That's it. That's right, Lynn. That's right. Boy, I noticed. You know, some people knew his name right away. Okay, so all right. So we are looking for v at, well, I want to be careful here. So in the previous problem, when I computed the derivative, I had f prime of 2. Okay, I had f prime of 2. Now, of course, my function isn't f, it's h. But I'm not doing h prime of 1. Okay, I want to find the velocity of the rock at 1 second. But I'm not doing h prime of 1. Instead of using 1, I'm going to use a. And the reason is I want to get a general formula for h prime of a, which would be the velocity at time a, the instantaneous velocity at time a. I want to get a formula for h prime of a in terms of a, and a could be any time. And then I'm going to use that formula to answer this question. I don't want to have to compute the derivative twice to find out the velocities at 1 second and then 4 seconds. So I'm just going to find a general formula for the derivative 1 and then use it. So this problem then, it works just like the last problem. This is the definition from the derivative. And as you know, you really learned 2 definitions for a derivative. This was one of the definitions, okay, for a derivative. And there was another definition also that you can define the derivative as, you know, the limit as x approaches a of the quotient f of x minus f of a over x minus a. That was another definition. Sometimes one definition is easier than the other to use. This definition here I have seen used more often in my experience, which is why I think that it is used a lot. Okay, so we're going to do this one this way. So okay, using this definition, h of a would be 10 times a minus 1.86 times a squared. I'm just putting in an a for my value of t. So we're at time a. And then h of a plus h would be 10 times a plus h minus 1.6 times a plus h quantity squared. Okay, so this is something you've done in the past. I mean, when you learned about functions, you sometimes would put interesting expressions in for the variable and might wonder, well, gee, why do I need that? Well, here's an example where you're actually using it. And then, of course, the next thing I have to do right is I have to write out what a plus h quantity squared is. And that's going to be a squared plus 2ah plus h squared, because that's a plus h times a plus h. Sorry. A plus h times a plus h. You FOIL that and you'll get a squared plus 2ah plus h squared. Okay, and then of course, I'm doing some math above. 10 times a plus h is 10a plus 10h. And then I distribute this minus here through the 10a and the negative 1.86a squared. And that gets me, what's there. So are there any questions up to here? How many of you find it helpful that I circle things and emphasize things with the marker? Is that helpful? Okay, I was curious. Okay, excellent. Good to hear. Thank you, Neil. Thank you, Nicholas. Thank you, everybody. All right. Well. So what comes next? I mean, let's say you're working on your homework here, and here you are. What has to come next? Combine. You have to simplify that numerator. Okay. So I mean, it's intuitive. That's what we have to do. We're trying to get this limit simplified, and so I do. This is my first step towards simplification. This is what I have here. And it might seem a little scary. All these terms. I mean, we got like 7 terms there. But if you do your work right, if you do the process right with derivatives, good things will happen. Some good things will happen. Do some good things happen here? Do some terms go away? Okay. What terms cancel out? The 10a, that's right, John, and everybody, Lynn, Nicholas, Z, Betswood. 10a's go out. Anything else? Ah, that's right. The 1.86a squared. That cancels out. You have a negative and a positive there. Okay. And so we're left then with this limit. Okay, so this is our h prime of a, right? This is our h prime of a here. And that's this limit. Okay. And can we simplify things a little bit here? One moment. Okay, never mind that. That's just spam. So the h can simplify out. Good. Divide the h, and you're left with this. So I could have put in an additional step here. I could have written, for instance, I could have written this numerator. I could have factored out the h and written the numerator as, well, yeah, oh, yeah, okay. And then, that's right, Nicholas. But I could factor out the h. So we have h times 10 minus 3.72 times a minus 1.86 times h. And then this h simplifies with that h, and I'll get this result here. Okay, and then of course we let the h goes to 0, and what's going to be left? As h goes to 0, what happens to this last term here? Goes to 0, and you're left with 10 minus 3.72a. All right, that is equal to your f prime of a. Or I'm sorry, I didn't mean f. Actually, I meant h, right? Because it's h. H prime of a. And remember, that is the velocity of the object, the velocity v of the object at time a. Well, so Nicholas, it doesn't, the starting point, the starting point, the fact that we, in the problem, we throw the rockward upward, and you know, it's going to have to come back down, right? Because Mars has some gravity, right? The h, like, so we're, the origin is where the ball like starts at, thrown up, and then comes back down. That determines the h function, but the derivative is not, it doesn't depend on that. Well, what I'm trying to say is the fact that you're starting it at the origin and it comes back down. I want to be a little bit careful here. It doesn't affect that. The h function is not. I want to be a little bit careful because I want to make sure. I want to make sure I'm saying the right thing. But the velocity at time t equals a doesn't depend on the origin. That's what I'm trying to say. And now Betsu is right. Now we're going to plug in 1 and 4. So may I go to the next page? Are we good? Okay, so now what we have is a general formula, the velocity at time A equals 10 minus 3.72 times A. And so that means I can find the velocity. And when I say velocity, I'm talking instantaneous velocity, because I'm computing the velocity at 1 second of the rock and the velocity of the rock after 4 seconds. And now that I have a general formula, I just plug in 1 and 4 into the formula, and that gets me my instantaneous rates, my velocities, instantaneous velocities. And this is why, this is actually a lead-in to section 2.7. So section 2.7, I'm not going to have a whole lot of time to discuss 2.7 likely today, but I'm not worried about it, because we could redo this problem, and instead of A, we could have an X, for instance. And this process is the same. Section 2.7 talks about the derivative as a function. But I'm comfortable, if you do 2.6 and you're comfortable with that, 2.7 you'll be able to do. And so I mean, we'll obviously cover 2.7 on Monday in more thoroughly, but you ought to be able to do some 2.7 questions. Now you'll notice in the velocity. There are units to these applied problems. The velocity is a derivative, okay? The velocity is a derivative, and a derivative is a rate. So a rate has a numerator and a denominator. Velocity, how many have heard of like velocity in meters per second? How many have just kind of heard that term just in passing in the world? You know, this person ran, you know, sure, in the Olympics, he or she ran, there you go, 50 feet per second, or the plane, it's traveling at 300 miles per hour, you know, that sort of thing. So velocities are rates, and the numerators is in terms of, like in this case, meters, and the denominators in terms of seconds. Well, velocity, what we're talking about here, Ian, are computing there are velocity vectors. There are vectors. Velocities, you'll learn in Calculus 3, multivariable calculus, and maybe you'll see it in physics that vectors represent forces and velocities. So a velocity can be in a certain direction, and that's a vector that points in that direction. But the length of the vector is actually the magnitude of the velocity, and we're computing magnitude velocities here. We're not dealing with vector velocities, but we are. But indeed, you'll see that the derivative is that the velocity of a vector velocity. I want to say this right. The velocity vector can be written in terms of, it's a derivative also, but it's a derivative of involving vector functions. So you'll have to wait till calculus. You have to wait till multivariable calculus for that. You're looking forward to that, Ian, I assume, right? How do we get 6.28 over 1? So okay, so what I did, John, was I wrote like 10 minus 3.72 times 1 is the same as 6.28. Okay, we know that's 6.28, and in fact, it's 6.28 meters per second, right? 6.28 meters per second. But when you have it written, like a lot of times velocities are written this way, but you have to understand that what that means is 6.28 meters per second is the same as 6.28 meters per 1 second. That's what that means. They mean exactly the same thing. Very good question. So like for the velocity after 4 seconds, that's negative 4.88 meters per second. But that then is negative 4.88 meters per 1 second. And it's helpful to see the derivative's written in the fraction form, because then it makes sense in terms of the picture. So, like for instance, at 1 second, I've drawn a picture of our I want to say our height function, the height of this object that was tossed up, and obviously the object goes up a certain amount and then it comes back down, right? Because you have gravity acting on it. So at 1 second, I'll draw the, at t equals 1, I'm going to draw a little dot right here. Okay, and then what I'm going to do is I'm going to draw a tangent line right there. So this is when t equals 1 second. That's where I drew the, whoops, that's where I drew the tangent line. So I've drawn a line tangent to the curve at t equals 1 second. That tangent line is the slope positive or negative? It's positive. And in fact, what's the slope of that tangent line? .28 meters per second. And the way you can think about that, if you want to even be more, make it more interesting, is in terms of units, t is in seconds, and the vertical axis, the units are meters. Okay, because height is in meters. So if you were to like draw a right triangle here, okay, this here would be what we call delta H. And the vertical distance there on that triangle, and it's a right triangle. And this distance here would be called delta T. Okay, and this triangle, let's say this the right way. Well, I want to say this the way I want to say it. Just give me a moment here. It's just something that you're going to see. It doesn't matter. No, it doesn't. It doesn't quite matter. I'm just going to put that there. In the future, you're going to see things like that where they draw. I don't want to get off on a tangent here. Notice the not nice thing to say for calculus, right? I don't want to get off on a tangent, but you're going to see in pictures where they have delta H over delta T, and the point is, if you let delta T get smaller, and the delta H is going to get smaller, and well, I'm going to just stop there. I'm going to just stop there with that. All right, now let me do one more thing here. Let me do one more thing. At the other value was 4, right? T equals 4, and I'll draw a tangent line right there. Through t equals 4. That's the tangent line passing through the point on the curve at t equals 4, or a equals 4. What's the slope there? Is the slope positive or negative for this second tangent line? Negative. And what's its value? Good, everybody. What's its value? What's its slope? What's the slope of the tangent line? Negative 4.88. Good. 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 Let me see here. There was a question. Oh, okay. Well, we have to continue on. Now we have to find out with which velocity the object's going to hit the surface of the moon, or of Mars. Okay, but are we good so far? All right. Well, let's see. So first what we have to find, of course, is when the rock hits the surface. How are we going to find when the rock hits the surface? How are we going to find the time when the rock hits the surface? Nicholas says set y equal to 0. Okay. Well, when you say set y equals to 0, what am I going to set equal to 0? I don't have a y in this problem, but we do have a height. Okay, so very good, Nicholas. So we're going to take h of t, okay, and we're going to set it equal to 0. Because I got to find the time when this rock hits the surface. Okay, so up to here should be good. And I'm going to ask you a question right here. So we're having a busy class today, that's for sure. Okay, now this is just an aside here, but when we get to 10.86 t squared minus 10t equals 0, sometimes students, what they want to do is they want to divide by the variable. Okay. If you divided by the variable, you would get 1.86t minus 10 equals 0. But is this allowed? Is this approach allowed? Nicholas says no. What's the problem with the approach? What's the problem? Don't copy that approach down. But, of course, you're going to get 1.86t minus 10 equals 0. But what's the problem with that? Can't I solve 1.86t minus 10 equals 0 and get t equals 5.4 seconds approximately? Can I do that? There's a problem with this approach. That's right, Nicholas. You lose the other time. You lose the other time. So when you do a problem like this, where you have to solve for t, you never want to divide by your variable. The only time you can do that, like in this case, you'd have to say t is not equal to 0. But in fact, t can equal 0, right? Because the rock is on the surface at the beginning, at time equals 0. But of course, naturally, we're interested in the later time, when time equals 10 divided by 1.86. So now we have time equals 10 divided by 1.86, which is about 5.4 seconds. That's when the rock's going to drop back down. and hit the surface of the moon. And now, how do we find the velocity? What do we have to do? At what speed is this object traveling when it hits the surface? Nicholas says -10. Hold on, Trevor has a question. Do I have a, take out the T. Oh, so what I did, Trevor, is over here, this step here, I just added the -10 to both sides. I went +10 here and +10 there. Obviously, I would do it underneath. And so I got 1.86t equals 10. Trevor, you're good? Okay, we just solved this little equation. And when you solve it, you'll get t equals 10 over 1.86. And so now what we have to do is substitute it in. So let's go to the last, whoops, hold on. I don't want to go there yet. So the velocity when the rock hits the surface is going to be, actually, it's not approximately, it's going to be equal to -10 meters per second. That's the velocity. And in this problem, what I did, since WebAssign is very picky on its answers, I actually put in 10 divided by 1.86. I actually used the exact value of t when I worked this out. You'll notice the velocity is negative. That's because why is the velocity negative? Because the ball is going what? The ball is moving down. That's right, Zoe. When the ball hits the surface of the Earth, it's been traveling down, and so we get a negative velocity. Now, sometimes you'll have velocity functions that describe a particle moving sideways. So in that case, if the particle's moving to the right, the velocity would be positive. If the particle's moving to the left, the velocity would be negative. Okay. How many of you have to take physics or are taking physics? Okay. Nicholas, Zoe, John, I'm sure there are quite a few of you. Kelvin. Okay, Anna took physics. Joe and Layla. Layla doesn't. Well, don't worry, if you have to take chemistry, you'll see, well, in differential equations, you'll see, well, derivatives are used everywhere in all applications. Economics, chemistry, computer science, everywhere. Okay, I'll move to the next example. Does everybody have this copied down all right? Okay, oh wait, all right, John, all right. Okay, very good, John. Very good, everybody. Okay, let's do another problem. So I'm making sure we're doing enough problems. I mean, you know, in 2.6, I want to just have a variety of problems so that you can be successful with the homework. And then again, section 2.7, I'm not worried about giving you some questions from there. You can do a little reading in section 2.7, and you're going to be fine. Yeah, I think you're going to be fine. Okay. So I'm trying to show you some applications because that's one reason you're here. Is because, well, big reason, right? You're going to be needing calculus in your fields. Okay, take a moment to copy this down. Okay, so I had actually never had heard of the term bolts of fabric. I mean, I know that, like, bolts for a bicycle, that sort of thing, but in this example, but bolts of fabric, I looked it up. It's a legitimate term. I mean, like, it's basically when fabric is in a roll, like a roll of fabric. Has anybody, oh, and there are lightning bolts too, like, yes. Has anybody ever heard of bolts of fabric before? Nicholas has? Okay. Uh, yeah, it was interesting. I had not, but at any rate, first time for Yaki. Okay. Well, so rolls of fabric. A manufacturer produces bolts or rolls of a fabric with a fixed width, and the cost of producing X yards of this fabric is C. The cost C is some function f of x dollars. So of course, the cost to produce, the cost function would be a function of how many yards of fabric you produce. So that makes sense. That makes sense. So this problem, you notice there's no formula for the cost function f. But they still ask some simple questions like, what would the units of the derivative be? And then what does it mean to say that f prime of 1,000 equals 9? And then which do you think's greater? The derivative for 50 yards of fabric or the derivative for 500 yards of fabric? Right. So I'd like to go to the solution, but I want to make sure, does everybody have this copied okay? Does anybody need more time? All right. Well, so again, units of the derivative, it's important because a lot of times students, they'll compute derivatives I'm talking now like applied problems. They'll compute derivatives, but they don't think about what the units mean. And the units are very important. Like for instance, the velocity. We just saw an example. So what do you think the units would be for the derivative here? What do you think the units are going to be? Okay, so we have yards per dollar, dollars per yard. So Ian and Kelvin, we have two different answers. I always like it when we get two different answers because it makes interesting conversation. But you're both right that the units are going to involve dollars and yards. Well, so let's take a look at the solution. So the derivative f prime of x can be interpreted, and this is yet another. Well, I want to say this the right way. So what like you see here, I'll let you copy up to here, and then I'll explain what I'm going to talk about. Oh well, and you had a 50-50 chance, right? Kelvin was right, but I appreciate all answers. Okay, now let me see here. Let me write something down here. I'm going to write this over here. Let me see here. This is a plus here. This is a plus. Okay. All right, Trevor. Hold on here. One moment. One moment. One moment, everybody. Okay, thank you, everybody. So, I want to say this the right way. No, let me hold on. Let me just write this again. I'm going to talk about all of this in just a moment here. It's kind of hard sometimes to write with this pen, but that's what I got. Just so long as you can read it, it doesn't have to be pretty. Good, Rodrigo's seen it okay. Okay, so what I have here, let me just write something in red here. I'll show you what I'm doing here in a moment. Okay, one moment. Okay, so in section 2.6, which is the section we're discussing now, this is the definition of the derivative. The derivative f prime of a equals the limit as h goes to 0 of the quotient f of a plus h minus f of a over h. But, and that's for a specific value of a number or a time. But in fact, the derivative can be, it can be thought of itself as a function. So this top formula here that I've written in blue, you notice it's the same as the red formula. The only difference is instead of a, I have an x. Instead of the number a, I have a variable x. But I can compute f prime of x the same way as I compute f prime of a. It's just in the end, my function, my derivative, will be a function of x. And that's what section 2.7, that's the jump that you make. So I think if you're good with computing derivatives in section 2.6, you ought to be good with 2.7. But in this problem now, what they're doing is they're saying, well, look, there are different ways to think about a derivative, but a derivative is always the difference of something in the numerator divided by the difference of something in the denominator. And a difference, oftentimes, they call a difference a delta. So in the numerator, for a derivative, for this problem where we're dealing with costs, change in costs, that's what delta C means, change in costs That's a change in costs okay, over a change in yards. Okay, so that's another way of thinking about a derivative. And it's helpful to think about it for this particular problem. Because what happens is they write down what f prime of x is. They write it down here. But instead of an h going to 0, they let delta x go to 0. Okay? So you notice that this definition here is the same as the definition you'll see in section 2.7. It's just instead of an h, they have a delta x in place of the h, and they let delta x go to 0. It's yet another definition of a derivative. But it's the same thing. But what they notice here is that what you should notice is that in the numerator, your difference in your two functions are the difference of two costs, because remember, C cost, which is in dollars, was equal to f of x. So anytime I have a function evaluated at x, whether it's x or x plus delta x, the units are dollars. Delta x, x itself, is in yards. So the unit for f prime of x, the units are in dollars per yard. Okay, and you're going to have like a multiple choice problem where you have to interpret the derivative, but it's in dollars per yard in this case. Okay, are there any questions on that? You probably didn't even need to see this here, but it is kind of nice to see the definition of the derivative. It justifies the units. All right, I'll go to the next page. I will try to finish this problem out. Is everybody good with this? We only have one page left, and it's going to be simple. Okay, so for B, the statement f prime of 1,000 equals 9. That's going to mean that after 1,000 yards of fabric have been manufactured, the rate at which production cost is increasing is $9 per yard. So the 9 is the value of a derivative. So that has that's a rate. That's a rate. The rate's not meters per second. It's dollars per yard. Dollars per yard. So at that instant, when the factory is produced 1,000 yards of fabric, the rate of cost is $9 per yard. So a lot of times people are used to thinking in terms of velocities. For like derivatives, velocity is the sort of the easiest example. But there are economic applications to derivatives as well. Right, Lynn. Right. Right. Well, that's the thing, Lynn, and that's why I'm going over this. It's gonna. The applications, I think, help reinforce understanding of the derivative. How many would agree with that? Okay, thank you, Nicholas. All right, thank you, Ian. Thank you, John. All right. The applications, Leila, reinforce the definition of the derivative. That's what I'm saying. In the last part here, we wanted to know whether the hold on here, where is it here? Part C was, which do you think is greater, f prime of 50 or f prime of 500? Well, the way you want to think about this is the rate at which production cost is increasing per yard is probably lower when x equals 500 as opposed to x equals 50 due to what's called economies of scale. That's an economics concept. Okay, it may not be true for when x is larger, but basically how many have noticed that, like if you go to, like when you go to like a place like Sam's Club or Costco, you can get goods at cheaper prices compared to like maybe, you know, Safeway or Giant. I mean, we all love Safeway and Giant. My brother works at Giant, but how many have noticed that when you buy in bulk, you can sometimes get things cheaper? Yeah, and that's right, Akuma. That's right, Joe. And that relates to this. So probably the rate of production costs would be lower when x equals 500. Maybe at 500 units, the cost is maybe you know, $10 per yard, but to produce 50 units is maybe $15 per yard. Okay, and it just has to do with it's a lot more efficient if you want to like bring like I think of boats and bringing goods over, like say from China to the U.S. They have big boats carrying lots of things, huge boats, not small boats, big boats. That's because the bigger, you know, it just turns out that it economies of scale, it's cheaper to do it that way. But I want to comment, it may not be true then as x gets larger and larger, because you have to pay people overtime and stuff like that the more you produce. So that's what I wanted to say on this problem. Let me stop the recording here.